All right, another Physics Teachers Are Awesome reaction. Today we have rotational motion part 2. So here we go.
Okay, so continuing our discussion of rotational kinematics, I'm going to talk about where the rotational kinematics equations come from. So we can think of having cylindrical coordinates here where we've got r, theta, and z as our coordinate system. And if we have simple rotational motion of a rigid body that's only undergoing rotational motion and is not translating.
Just want a quick comment on the setup. So it's portrait instead of landscape, which is useful because that's exactly, well, typically the shape of the notes the students might be taking. So I think that there's actually some real value to that. Though the problem with YouTube, of course, is that they're always going to put these gigantic black things on the left and right. So that's really more of a YouTube problem, I think. But the dots are useful. They're a little bit less annoying than like graph paper. So, but it helps you really stay aligned. So that's pretty cool. It's definitely a pressure sensitive writing. So that's really cool. Let's see if we can see the mouse or the pointer when they're not writing. Let's just watch for a little bit.
Then theta is the only part of this that is a function of time. Okay, and if we have kinematics, what that means is that d theta.
So just a couple of comments. First of all, saying that only theta is going to be a function of time means that we're really, looking at rigid body rotation, right? We're not letting like some particle, get closer in or anything like that. And you can tell that this is a calculus-based course. I'm guessing this is a college course. I actually don't know. But the other thing I was going to say is we can't see the pointer unless she's actually writing, which kind of stinks, but I haven't yet found a really good system that does that well. I just like to point it out. But I think that usually in that case, people, the instructors or whatever, are able to really help the students understand what they should be paying attention to.
d theta of t dt is omega, which is also a function of time.
Ooh.
And then d omega dt is alpha. This is constant. Okay, that's what we mean by kinematics. And so let's take this and see what other results we can get out of it. So if we start with this equation and integrate both sides, right?
Nice.
Then we have our first kinematic equation. We're going to find that omega is omega naught plus alpha times t minus t naught.
Nice.
Right? Because our alpha is a constant, so the integration of that is just alpha times t. And then we can think of this as that omega is alpha t plus some constant. And we want to set our constant such that at time t naught, omega naught, omega equals omega naught. So that's where this equation comes from.
So that was really cool. So, I mean, technically she could have put, the limits on the integral and said that's where all of this comes from. But I really like this, right? Like, there's just some arbitrary constant which students, calculus students understand why that exists. But it's not arbitrary in a physics problem. We have the freedom to choose it to be as useful as possible. And in fact, what we want it to do is to make sure that this is true. So I think that was really cool.
We can then integrate this one again to get a function in terms of theta. So here on the left we'll have theta, a function of time, and then we're going to find that this is omega naught t minus t naught 1/2 alpha t minus t naught squared. Again, we can think of this as actually.
So it's interesting, right? So it's not immediately clear why this term would show up. If she hadn't been doing the constants, this just would have been a t. This would have been t squared easy. So, this, I think, it really helps students understand that, look, we're always measuring with respect to some start time rather than leaving it 0. I think this is really, really nice to be able to sort of always be able to compare it to some starting point. So we have some initial theta, some initial omega, and some initial time. But strictly from integrating this, the students would integrate this term first, and then they would integrate this term, and then ultimately they'd be collecting it all. And it would, it'd take a couple of steps to get here, but I think that it's just so clear what's happening. This time difference is really all that matters.
Finding omega naught t plus 1/2 alpha t squared plus some constant, and then we're going to set our constant such that, I don't know where this VHS thing came from. Oops. We're going to set our constant such that at time t equals t naught, theta equals theta naught, and the way to do that is by putting everything in terms of these constants.
Very cool.
Shown.
Very cool. Sorry, I should have let her just do it.
And then our last kinematic equation eliminates, for our last rotational kinematic equation is eliminate t. So substitute in our omega equals omega naught plus alpha t minus t naught into the theta equation. So if we solve for t minus t naught, so t minus t naught is omega minus omega naught over alpha. And then if we substitute that in for t naught above, then we will have theta equals theta naught plus omega times omega minus omega naught over alpha plus 1/2 alpha omega minus omega naught over alpha squared, and we can rearrange that to get our last kinematic equation. So I'm not going to share the details of this algebra here, but this would be the result. And all this derivation should look very familiar. It's very similar to how we derived the linear kinematic equations before.
So I'll say it now, just like I've said so many times before, this equation to me is a work energy equation, and so algebraically you get there here. But it's so interesting that if you put in a 1/2 I everywhere, you realize that you're just conserving rotational kinetic energy with this. And so I really, really liked this. It looks like we're just about done here. So I'll just comment that she's not directly doing the integrals. She's saying, you can sort of see where this stuff is coming from. You can understand. And right at the end there, you can hear her saying that, man, this just should look so familiar, right? Just think about it. We have a straightforward system where the second derivative is constant. And so then we can just integrate up. And so no surprise, we're going to get some t squareds. We're going to get some t's. And then we're going to have all the tools we need to be able to go do some really, really interesting problems. So I think that was really cool. I like the setup, but I think that it was quite clear, of course, and I thought this was great. All right, everybody, well, I hope you have a great day, and remember, physics teachers are awesome.